So this video is going to be a quick guide on how to approach an LR-ER problem in a step-by-step manner. If you follow these steps for every problem involving limiting and excess reagents in thermochemistry, you will be fine and you will get the right answer every single time. We're going to start with the question itself. So a 1 gram strip of magnesium metal is added to 150 milliliters of 0.3 mole per liter hydrochloric acid in a simple calorimeter. The solution temperature increases by 3.9 degrees as a result of the reaction. What is the molar enthalpy of reaction? So you might not be able to recognize right away that this is an LR-ER problem. And so for any calorimetry problem or any enthalpy problem, step 1 is going to be to write a balanced reaction. So we're going to do that now. In this reaction, solid magnesium is going to react with hydrochloric acid. And this is going to be a double or a single replacement reaction. So we'll make magnesium chloride and hydrogen gas, and hydrogen is diatomic. So to balance this, we need 2 hydrochloric acids. We have our balanced reaction. Our next step is going to be to list everything that we know about the reaction. By listing our known quantities, we'll determine, do we have enough information to determine LR-ER, or is this a straightforward question? So for magnesium, we know that the mass we have of magnesium is 1.0 grams. We can always look up the molar mass from the periodic table, which is 24.31 grams per mole. For hydrochloric acid, we have a concentration of 0.3 moles per liter and a volume of 150 milliliters or 0.15 liters. For both of these, what we can see is we have enough information to solve for moles. So if we have mass and molar mass, we can solve for the number of moles of a solid. If we have concentration and volume, we can solve for the number of moles of a solution. By being able to solve for the moles of both reactions, this is an LR-ER problem. All right, so this is going to bring us to step 3 in this reaction. And so here, our number of moles is 0.041 moles of magnesium. For solutions, concentration times volume will give us moles. So 0.3 times 0.15, and we get 0.045 moles of solution, or moles of HCl. This is not a comparable number. We cannot compare these numbers directly because they have different coefficients. So we need twice as much HCl as we do magnesium. The way to compare the number of moles is to divide by the coefficient for each reactant. So we're going to take the numbers that we currently have and we're going to divide by the the respective coefficients. So we'll divide magnesium by 1 and we get 0.04, and we're going to divide HCl by 2 and we'll get 0.02 with some extra numbers on the bottom. So we can these two numbers that we have now, these are directly comparable. And the smaller of these two numbers corresponds to our limiting reagent. So this means that HCl is our limiting reagent. It will run out first and it will determine how much heat is produced. We're not going to use the numbers we just solved. So these numbers at the bottom, these are not going to be used again. Those were only determined for comparison. we're going to carry this 0.045 moles per liter forward for our next calculation. Okay, so now this becomes just our typical molar enthalpy question. So molar enthalpy will always use the same formula. N delta RHM, this is our system. So in this case, this is going to correspond to the actual molecules of HCl. That's going to equal negative MC delta T. That's our surroundings. That's going to correspond to water. Now in this problem, the water is coming from the HCl solution. Because most of an aqueous solution is just water, there's very few molecules of the actual compound compared to the amount of water that's present. So we know the number of moles, we found that last time. So if we want at this point, we can plug in our numbers. So we know that we have 0.045 moles of HCl, and we're solving for this molar enthalpy piece. So I'm just going to highlight that for us here. So that's what we're going to be solving for. The mass of water is the same as the mass of the solution of HCl, so 150 grams of water, because we have 150 milliliters. Our specific heat capacity, we're going to use those assumptions we learned earlier, so the same as water, and our temperature change is 3.9 degrees Celsius. So on the right side of our equation here, this is the energy gained by the water. And in doing this math, so I'm just going to do this, kind of the math a bit separate. So we're going to have 0.045 moles over here still, multiplied by our molar enthalpy, and we get negative 2,451.15 joules. That's the energy that was gained by the water. So we want to figure out the energy that was given off per mole of our reactant. So we're going to divide both sides of our reaction by the number of moles of HCl that actually reacted. And so what we can see is that our moles will cancel on the left, and we get a total enthalpy, or a molar enthalpy, of negative 54,470 joules per mole. And that's joules per mole of HCl. Now, normally we're going to put this into kilojoules, and we get two significant digits from our temperature here. Because we didn't actually use this 1 gram, it doesn't contribute to sig digs. So this gives us 2 sig digs, 3.9. And so our answer is going to be negative 54 kilojoules per mole. So your problems may look a little bit different, but if you start to follow those steps as you do them, you'll see that it's the same process for each problem you're solving. And that will make these complex LR-ER problems a lot more approachable for you.